So LeetCode 1649 creates sorted array through instructions. So in this problem, you're given an integer array of instructions, which are just numbers, and you need to insert them into a nums container. And you need to keep this nums container sorted. And at every step, you have a cost, which is the minimum between the number of numbers that are strictly less than your current number and the number of numbers that are strictly greater than your current number. Okay? So for example, here we need to insert 1 into an empty container. What is the number of numbers that are strictly less than 1? It's 0. What is the number of numbers that are strictly greater than 1? It's 0. So the cost is 0. And so on and so on. And at a certain point you are like this. So your nums container is like this. And you now need to insert 2 because it's the last number that you need to insert. How many numbers strictly less than 2? There's only 1. So the cost there is 1. How many numbers strictly greater than 2? There are these 2, so the cost is 2, and so the minimum is 1, and so the cost is 1. And so at the end, your total cost of all of the operations is 1. Okay, so if you try solving this with a trivial, like not trivial, but naive solution, which maybe uses binary search to find the amount of numbers that are less than or greater than, it's not going to work. It's going to give you a time limit exceeded. I implemented that here. It's using a binary search and splice to insert into the nums array, and it doesn't work. It doesn't even reach the last test case. So if you really want to get accepted on this, keep in mind it's a hard problem. You're going to have to use a less known data structure. So there are 2 data structures that can give you accepted on this problem, and one of them is easily understandable, and the other one is really going to confuse you, but it's the optimal one. So the one that is easy to understand is the square root decomposition technique. So that's a much easier technique than the Fenwick tree, which is the second way you can solve this problem, and it's optimal. It has a better asymptotic time complexity, but it's like dark magic. You cannot understand it without spending a lot of time into it. So in this implementation, in this solution of this problem, we're going to use the Fenwick tree, but we're not going to explain exactly how it works. So we're going to treat it as a black box, and if you really want to understand how it works, you're going to have to watch other videos on the topic. Okay, so here we're just going to use its function. We're just basically going to paste in an implementation of the Fenwick tree and just use it for the sake of this problem. Okay, so we're going to start with an empty result, which is going to be our return value, and at the end obviously we're going to return it, and we're going to have our array that represents the Fenwick tree. Okay, and keep in mind that the Fenwick tree is always 1 based, so you need to add 1 to the upper bound of the length, which is 10 to the power of 5. So here we have 10 to the power of 5 plus 1. Okay, so this is going to be our auxiliary array that basically doesn't do anything other than storing the Fenwick tree information. Okay, and now, sorry about that. So now you have your loop that goes through all of the elements in your instructions array. And you take the element and you add to your total cost the minimum between the number of numbers that are less or equal to your current value minus 1. And that equates to the number of numbers that are strictly less than your current number. Okay, so again, let's say it one more time. So get is going to be a function of our Fenwick tree that returns, it takes a parameter, let's call that parameter x, right? And get of x returns the amount of numbers that are less or equal to x. So if you want to instead get the amount of numbers that are strictly less than x, then you're going to have to call get of x minus 1. Okay, and that's what we do here. And the other cost is I minus get of the current element. And what this does is I is also keeping track, other than the index of A array, is also keeping track of the length of nums. Because at every step you're adding 1 number into your nums array, and so I at the beginning is 0, because the length of nums is 0 at the beginning, it's an empty container, and then at every step you add 1 more number, so I also gets incremented. So by coincidence, I is also the length of nums, and so you're doing, basically you can substitute this with nums.length. So you're doing nums.length minus get the number of numbers that are less or equal to A of I. And so that gives you the amount of numbers that are strictly greater to a of I, okay? Because you take all of the elements and you remove the number of elements that are less than or equal to a of I. So you're only left with the amount of elements that are strictly greater than a of I, okay? Right, so this is adding the cost of the current element. Then you don't forget to do the modulo by 10 to the, I forgot what it is, 10 to the 9 plus 7, okay? And then don't forget to actually insert the num, the current instruction, into the nums array. And so to do that, we're going to have a dedicated function, which is update a of I. Okay, so this would actually work if you had already implemented the get and update function, maybe from an external module or something like that from a library, but actually we have to implement them ourselves. So I'm basically going to paste in the code and very briefly talk about it. But again, if you want to understand how this function works, you're going to have to watch a in-depth video about the Fenwick tree. Okay, so here are the get and update functions. So the update function is showcasing the direct relationship. So given an index in your auxiliary array, the way you can travel to your parents, to your ancestors, is by adding your least significant one digit in your binary representation. So here, for example, let's say that x in binary is something like 1010, something like that, right? Then this is going to give the last one going towards the right, that is in its binary representation. And it's going to add that same one to itself. And so by doing that, you're basically shifting all of the ones to the left up until there is only one digit in your number, in your binary representation. And then you're starting to double yourself, okay? So that's exactly the definition of the relationship between node and ancestor node in our array. So that's how exactly an array can represent a tree, right? And then the get function is doing kind of the same thing, but instead of adding, it's subtracting, right? So it's traversing the tree in the opposite direction, basically. And you also have a cumulative result, which at the end, you always update it for every iteration, and at the end, you just return it. And always keep in mind that the Fenwick tree is 1 indexed. So you do not start with 0, you start with the index 1. Okay, so now is the time to go ahead and watch a in-depth video on how the Fenwick tree works, if you truly want to understand this, or if you're fine by just using it as a black box, this is fine already. And just one more thing, basically all of the tutorials on Fenwick trees use prefix sum or range sum to showcase the Fenwick tree. And here we're not doing the prefix sum or range sum, we're actually doing the count of the numbers that are less or equal to our current number. But that basically is equal, this problem is kind of equal to the prefix sum if you pretend that all of the values in the array are ones, right? Because the prefix sum of all of the numbers from index 0 to 1000 is equal to the count of numbers that are in the array that are less than 1000, right? At least that's my understanding of why you can use a Fenwick tree, even though the Fenwick tree is usually used for range sum. Okay, so that's it for me today. Hopefully this has been helpful to you, and thanks for watching. Bye.